Okay. Then we're going to hear about the paper on WebAssembly by a whole mess of people.
Yes.
That was
Google, Microsoft, and
yeah.
Apple.
So it's an interesting paper, and you'll probably talk more about this, but it brings together basically the 4 big browser manufacturers. And I remember this was a big deal. I was actually, this was, I think, TLDI 2017, this paper first appeared. I was actually at the talk. It seemed like a big deal at the time that all of these people were coming together to propose this. So, take it away.
Okay, so like the general trend, if you haven't noticed, for the past decade or so, is more and more stuff that used to be like desktop applications, like games, modeling software, creative tools. They've all kind of been moving to the browser for a variety of reasons. But there's been a problem because like the only real programming language on the internet is JavaScript, and JavaScript was designed in a week by some like crazy guy at Netscape in the 90s. And like because it's been ubiquitous and it's got so many lines of code being run every day, like browsers have gotten really good at optimizing it, and like it's in some cases even faster than like Go and the compiled languages, right? But it's still like problematic. It's got a garbage collector and stuff like that, right? So we've gotten around this in the past when JavaScript was even worse with things like Flash and Java, and then Microsoft had its own ActiveX thing, and then Native Client, a bunch of others, which they all just suck for various reasons. Like for example, like security or trust model being impossible to get into, or platform specific. But one that's kind of interesting is ASM.js. And they actually just use JavaScript and rely on the fact that browsers are super good at optimizing the code. So like you have, what you do is you just have like A, B, C, or 0, and the browser is smart enough to say, hey, that's an integer, because you're doing the bitwise OR with 0. And that's good, but it still has the same problems. It's not perfect. So this is why they designed WebAssembly, and so they had like 4 main goals, which were safe, fast, portable, and compact. And this is where they elaborate on that. And the main reasons is this was designed for a browser, but if you've seen like Node.js, like things get used outside the browser too, and that's just as important. And even if it's just in the browser, security, privacy, all that are like super important because all your bank and stuff like that is going to be using it too. So those are the main things. It's got to be in a browser and it's got to be used a lot. So skipping into semantics, I'll go over the first 2 types, and then I'll kind of like elaborate on the rest of this mess. Okay, so like the 4 value types in the top. So the I32, this one. I32, I64, those are the types that correspond with what's stored in like registers on your ARM CPU. So like maybe x86 has that integer 8 type register, but ARM doesn't, so they had to get the weakest link in there. So skipping to, I'm going to cover the rest of it. I just wanted to show like, okay, so all of this, these are, as the paper describes them, they have obvious semantics, but you have a few things here. So you have unary integer operators, float operators, and then you have binary integer operators, right? And so it's important to note that they have, so you don't have distinction between signed and unsigned values, right? So notice you have I32, you don't have U32, right? So it just says, okay, you have signed and unsigned versions of the division, remainder, and right shift operators along with the comparisons. And that's how you handle unsigned distinction. And then see the SX here type, or it's not a type, it's just an extension to the operator. And then I guess we can go to the rest of it. So WebAssembly programs are binaries. They're contained in what's called a module, and it contains basically all the statics of the of your program. So like your function definitions, your imports, your globals, stuff like that, right? So you can see here, this is where the semantics of the module are defined, right? So module, it consists of a list of functions, a list of globals, a table, potentially, or a memory. And so I will talk about tables first. Okay, so one of the goals was safety, and function pointers are not safe. So what they did is said you have to use a table, so you store, you put the functions into a table, and then you use an operator called call indirect to call the function from the table. And you just use the index that is put into the table. So it's kind of messy and painful to work with, especially if you're coming from like C, but it kind of works. And then globals, so those are variables that are shared between functions, static variables in C, straightforward. And then linear memory, this is kind of a weirder one. If you've taken an operating systems class and you had to implement malloc, that's basically how linear memory works in WebAssembly. It doesn't give you a malloc predefined. You have to manage your own entire heap space, right?
So it gives you an S break?
Yes, exactly. Right. It has grow memory and current memory. So that'd be equivalent to S break, grow memory. So you start out, you define your memory's object with, yes, the memory operator, and you give it a number of pages, which are denoted in 64 kebibytes. If you run out of space, you have to do memory.grow, or else you'll get a out of bounds error, and we need to look it up. So reading and writing is through load and store. So with this, you have to type in the type of the value, and the address and an offset. The offset is usually optional. It just assumes it's 0, but you have to give an offset in these semantics. That is syntax. And then, so those are the main parts of the module. I will talk about the rest of those operators here with an example, because this is probably the weirdest thing with it. So normally, if you've done assembly, you have a labels and breaks or branches and stuff, right? Yes. I probably should have thought about the black background, right? But what's it? That's dangerous, right? If you branch into the middle of a multi-byte operator, right? That kind of sucks. Or if you branch into another function, that's also not good. So what they did is made it a structured assembly language as well, which has its own pitfalls, right? You can't do everything that you can do with a, there are algorithms to convert between when you have an x86 or whatever with blind branching to outside of it, but you have two different types of structures, right? You have the loops and blocks. And so with the block, when you branch, it branches out. So here, brf0. So what it's doing is it's getting the first parameter, or first local, which happens to be our input. So this is the absolute value function. And it compares it with 0, and if it's less than 0, it branches here, where it negates it. And it implicitly returns it. So here, brf, the condition, and branching out did this, right? And then br1, it branches out of both of these, right? So the way they have this, it's described as called a control stack. So that's why you have the 0, it branches 0 off the stack to the end of this. Now it branches 1 off, so it's that, right?
So it's like pretty much arbitrarily exiting
Yes.
some amount of scopes.
Yeah, so this is like your break operator, right?
Yeah.
And then loop, it's the opposite way. So if you do break in a loop, so here this is a factorial. If it's less than, or if it's greater than 2, it goes back to the top and does it again, right? And then once it's done, it gets the sum and returns it. So that's not too bad. Is there anything else here that's interesting?
How does syntax for imports and exports work? I'm seeing them like on
Yeah.
tables and memories. And
Very-
it looks easier.
Yeah, so you have, this is actually missing something too. So basically imports, you have the name, so it has 2 names, right? The first one is like a scope, so when you have when you instantiate your WebAssembly module, you link it with your host environment, right? So you have a scope for like JavaScript functions, and you include it there, and then if you have another WebAssembly module you want to link it with, you include that module with the namespace. So this would be like WebAssembly program 1, and then the input from that program, or one of that program's exports, right? And then exports are just, this.instance.exports, right?
But why are they like associated with the other 4 items rather than just being their own thing within a module?
They are. There are their own thing in the module.
I'm seeing like it says X star and in with the definitions.
Yes. So, I see what you mean. Okay, yeah. So this is how they made it work with this stuff, right? So, this means that you can export any of these things,
Okay.
right?
So you're exporting the item you're defining, and then the imports are.
Yeah, they go on the top, but this also, it should have a type, right? So you can't just import a function, you have to import a function with a specific type, and then it gets added to your list of functions so that you can call function 0.
It's like you would have extern in C, where you're saying this thing exists, but it's not part of this module.
It's kind of like, it's like extern,
Okay.
but much stupider. Like it just uses numbers instead of like symbols.
I think I get it.
Yeah.
You do have to specify the name of the module from which you import something.
Yeah.
Yeah.
Oh, I
it's
see.
It's not quite like extern where you
But-
just like it exists and you just import it.
Okay. Yeah, I see that difference.
Also, keep in mind at the start, like the notation's a little confusing, but they use like this regex notation at the start.
So it's saying it can be exported 0 or 2 or however many times.
You could have other
Different
exports before
names.
it.
Yeah, it just means like 0 or more exports.
Yeah,
So
sure.
that means you don't have to like export something that you
Yeah.
import, for example. Like you just import it.
There's no separate alternative with no export because the star covers that.
Yeah.
Yeah, so going into the semantics. So they have this really complex store object, but so you have the instances, which they wanted to have this to be like in C, you can have one or more DLLs that you include, or one or more static libraries that you link with. So they have more than one instance you can have, and of course each of those instances has its own tables and its own memories. And I don't know if I said this before, you can only have one table or only one memory with each module. They all correspond with each other in those lists. And then in each instance you have a bunch of function definitions, globals, a table, or memory, or and a memory. And then in each table instance you have a function and a index for the function, which is, or the instance that it's defined for. And that's what the CL closure means. And then in your memory it's just a list of bytes, which is what the B star means. So and then so that's where it defines closures as an instance and a function for the body of the function. And it also says that you can't have imports there. So it's the original, it always points to the original implementation, not like a reference to a function, which would be bad. And then values. they are denoted as the type of the value, which usually is parametric or whatever, and or polymorphic, and then const, and then C. So it's just like if you're defining it in a program. And then they added some other operators because they wanted to be more general. So like trap, it's anything that causes it to stop, terminate running. And usually that shows up as like in JavaScript you get an exception and you have to handle it. And your WebAssembly code is just broken, but you just keep going. And then call, it removes the whole call indirect thing, and it calls the actual function in the actual instance. So that's how they handle that. And then labels. So labels is how they handle the structures. So like a block would be set to a label with an end. So like all the instructions that are within the block and then the label. And then locals are the instance and then a bunch of values that are associated with that scope or with that function, and the instructions over which those are defined. And then this goes into more detail on the locals for the labels, and it's kind of messy, but yeah, this is what's simulating or making so they don't have to explicitly define a control stack. And then the steps here is more or less saying you only step the stuff that's in the current block or scope. So like you don't go outside of it, right? And then here it only one of the other things with WebAssembly is like with C, you can just say like have a function that has like you have your age and like a name, and then their social security number. And then that's also a chart. And if you call a function with the name, you get the address for this stack, and then you can, whoever, if that function is compromised, they can get this user's social security number. Or even if they didn't use pointers, because it's easy to pick up pointers, they could just look back in the call stack and get these, secret numbers. So WebAssembly doesn't have that, so they have locals. I didn't really talk about that here, but you saw in there where they have the locals there. That means you can't explicitly read and write from the call stack.
You can only do it with that, and that can only go as far as your own arguments.
Yeah, no, you can do, if you notice here, we actually defined another local, right? And so
Okay.
it's also, in addition to being for safety and security and stuff, it has the benefit of allowing the just-in-time compilers and stuff to convert those locals into registers, right? Because then you wouldn't have to rely on it being on the stack and being addressable and stuff like that. So there's a number of benefits. But anyway, that's the second one. It says only the locals within this function will be changed when you set. And this is this notation here. It's the store, which is all this mess, and then the local definitions, and then the list of instructions. So yeah. And these are all the ones that they said were obvious. And I can, if the syntax looks weird, I can do one of the version of it with our one we covered, because it shows why it's so much more efficient to write like that. Alright, then so this is half of the first one, right? Or this part here. So this is that line there as our syntax, so it is basically the same thing. But this says if there exists a result for binary operation, which is obviously defined, then these two values with that operator steps to the result. And then if it's not defined, you have to write another one of these, which I'm not going to do, but it traps. So if you divide by 0, it traps. And the rest of them are very similar. Unreachable is just a trap. That's your like only easy trap to use. No up does nothing. Drop removes the value from the stack, and it selects like CMOF, and it's like branchless selection. And branching, this is how they have it here. So interesting to note, branch if it steps to a branch, and then if it is the case is false, it just steps to empty. And then the loop, it substitutes itself with another loop, and notice that it has a type there too. And if statements are also straightforward. There's a lot of these, so I'm not going to go into too much detail on all of them. Calls are straightforward. They all step to different call expressions. So like if you call indirect to an index that's not valid on the call table or on the table, then it traps. And then and the rest of these we said were not too fancy, or not too vital. And then locals, pretty straightforward. So here, J, so it takes values up to J, and then puts another, or it takes a local from that. And so, okay, sorry. So you have a function with locals that go all the way up from all the way to J, and then you have V, and then V2K, and then you have V2 and set local, and then it steps to nothing but with that value and placed in the new value that you passed into it. And then T, it's like the T command in Unix. It passes the value, and it's like if you have a set and then a get right after it, you can just replace it with the T. It's like optimization kind of. And then you don't have that with the globals, but this notation is kind of weird, but it means for the ith index, ith instance, select the global, the jth global in that instance. That's how they did like nested sub things, and there's an even weirder one with memory. So they did a little bit. They said in their notation abuse, but so this is what I was talking about with memory. So they have so if the ith instance of memory at byte index k plus offset, so they pass in you pass in the i32, which pointers are 32 bits in WebAssembly. You pass in that pointer with the address and offset. So it goes into memory and pulls out T, which is the size of type T bytes, and if that whole range of values from k plus O to k plus O plus size of T are defined, then it defines a new value, which their value judgment is just the WebAssembly way of constructing it. So t.const, and it defines it with those bytes. And then the same thing for sign types. And if it's not defined in traps, and storing, it does this. So if you can define a store such that those bytes are defined as the bits, from here, then it steps to the new store with nothing else, right? So it doesn't have a new operation vector, right?
What would it mean to be unable to do so?
If the address is out of bounds.
I see.
So like,
Sure.
yeah. That's another weird thing with WebAssembly. You don't have null, which usually 0 is undefined, or give you a cycle.
But no, you just have a
Yeah.
buffer that is somewhere and
Right. So in your stack pointer, you put it like somewhere before, and then if it goes over, it gets negative or it
you
goes
don't
to
have like
infinity.
an entire RAM. You
Right.
just have a heap that starts
Kind
at
of.
0.
Yeah, it starts with 0. Yeah. So right. Then the current memory, this star means all the bytes, right? So this is the size of the entire memory, and that's what it gives you. Divided by 64 KB, assuming that it has it. The grow memory returns -1 if it can't, so it doesn't trap, because you could genuinely run out of RAM, and that could be a condition you want to check for. I'll give it to you.
Yeah, so that was the small step semantics for WebAssembly, but a huge component about WebAssembly is the fact that it has a pretty robust type system, and that's what helps it guarantee a lot of its benefits with security, memory safety, and ability to access code and whatnot. So in the type checker, there's a context called C, which contains the list of function types, the list of functions, the list of globals, the function table if it's been defined, the memory if it's been defined, the list of locals, and then a sort of stack of labels, and then the return type for a function if it's been defined. And then there's a judgment in the type checker that pretty much states that an instruction E under context C has a type function.
So.
And so using this judgment, we can pretty much type every single instruction that's provided in WebAssembly. So the most basic example is typing a const instruction.
You can also erase the breakpoint.
I'll do it if I need to. Which is it's an axiom which pretty much states that under any context you have t.const C as a type of epsilon arrow t. And this epsilon basically means nothing. And so the way that these function types work is the left-hand side is what it expects to be at the end of the stack. And then the right-hand side is what it expects to be at the end of the stack after executing the function. And so, so this type T can be anything, any of the 4 types. So I32 /64 or F32 /64, and then you can use this to declare constant values and then store them on the stack. Another basic example is the binary operation, which is also an axiom which states that under context C, any binary operation on type T, this instruction has function type T arrow T, which pretty much means when you execute this instruction, it's expecting 2 values of type T to be at the end of the stack. Once you execute it, there's only going to be 1 value of type T because it pops these 2 values, performs the operation, then appends this value to the stack. And so these typing instructions help WebAssembly have this sort of structured stack control flow, where at any point in the program, it knows exactly what this stack is going to look like. And this helps a lot with compilation. And other interesting examples that I could go over for loop equals different blocks. We have a block. From the context C, we define a block as block, and then you say what the type of the block is, which is a function type, TF, and then the contents of the block, which are instructions E star, and then end, which denotes the end of the block. Okay. And in order to type this, we have to verify first that, well, first we can destructure TF into the left-hand side and right-hand side of the type function as T sub 1, or T sub 1 n, arrow T sub 2 n, which pretty much means that the input has n type parameters, the output has m type n values of type T sub 2. And then what you want to do after that also is append a new label to the context. And this label has to have a type associated with it. And this type, for a basic block statement, a label has to have the type of what it expects to be at the end of the stack once you branch out of that block. Right? And since this block has a type function that's equivalent to T sub 1 n, arrow T sub 2 n, that means at the end of the block it expects to have T sub 2 n at the end of the stack. So the type is.
Does that mean that no matter what happens within a block, it should have the same effect on the stack in terms of what types are on it?
Right.
And so the type associated with this label should be T sub 2 n. And then this has to entail that the contents, which are the instructions of this block, also has type T sub n. Right, and the reason why we want to append that label is so that if we perform a branch within this block or within any block nested within this block, and we branch to this block, we want to make sure that we read that label and we can verify that the contents of the stack match what this block is expecting once it finishes. And this also applies to loop statements. However, there's something slightly different with loop statements when you write a similar rule for loop statements because of the way that branch statements work in a loop block. So this is how it would work. So if you have a loop instruction, which is defined as loop, and then function type, and like instruction contents, and end, like a value. Let's see if we type this as a function type. Right, in order to type this, it's pretty similar to this, except for one difference. First, you destructure function type for convenience sake. But then the label that you append to the context is not should not have the type of T sub 2n. It should have the type of T sub 1n. And the reason for that is because if you branch out of a loop, it doesn't branch to the end of the loop, it branches to the start of the loop. And that's how loops work in WebAssembly, as Kate mentioned.
So it's saying if the iteration continues, it has to be in the same. It has to be in the initial state, but when it exits, it will be in the M sub 2 state.
Yes.
I see.
Right. Yeah. Because it can either exit via wrapping a block around this loop and then branching to the block outside a loop, or the loop can just pass through execution, at which point you know it's going to have a T sub 2.
So you need to like define a wrapping block and then break one to terminate the loop.
You can do that, or
That's
you
what
can
the
just.
semantics did. Yeah.
I see.
That's one way to do it, or you can just let the loop go through. Because if you don't branch within the loop, it will just pass
Oh,
through.
and a branch 0 inside a loop is like a continue.
Yes.
I see.
Yeah, that's exactly how that feature defined it, actually. Yeah, so this pretty much means that if you repeat the loop, it expects to have the input types at the end of the stack over again, which makes sense. So this would then have the type TF. And then, So now that I covered blocks and loops, I'll also cover the typing for branch tables. So now that we have the typing rules for appending labels to the context, how do we utilize those labels? And that's where the branch typing rules come in. So for a normal branch, which is just BR, and then the label index I. What this does is we have to determine what the type is for the label associated with this label index I. And how that works is you just access it via the syntax. And the way that the label indexing works is it's bottom up, right? So since it's a stack, if you did BR0, this would access the last label. Right, so the most recent label or like the most recent block or loop that you're in. So that helps for convenience sake with syntax. And then, yeah, so under this context C, once you determine what the type of label is, you can say that the type of this branch statement, since it's branching definitively, it's a non-conditional branch, it's going to have a type T sub 1 star, T star, arrow, T sub 2 star. And so these T sub 1 and T sub 2 star are just arbitrary, those are just sort of extensions, or it's just notation for what's in the stack already before T star. And so what this is saying is, when you branch, you have to have whatever the labels, like whatever the block or loop is expecting at the end, which is T star on the stack. And then once you branch, it will go to like another branch, like another stack state T sub 2 star, which isn't defined, but it depends on whatever is after the branch statement. And then branch if is slightly different. I'm a little bit confused as to whether or not they made a typo in their rule. But yeah, me and Tate were discussing this before class. We're not quite sure. But
I think it's because BR if steps to BR, but
oh yeah, that's
I'm not sure.
yeah. So how BR if works is it takes in the condition variable, which is like a 32-bit integer, which is either 0 or 1, as one of its operands on the stack. And then it also statically takes in this label index I. And it's similar to the previous rule in that if the type expected at the end of this ith label is T star, then the type of this conditional branch is just T star I32 arrow T star. The reason for that is because this I32 is the condition variable that BR if reads from the stack to determine whether or not it should branch. And the reason why it keeps the stack the same, like except for the I32, is because one, BR if steps to a normal branch. Another thing is that BR if doesn't always branch. It's possible that the condition fails, and so it just doesn't branch and it just steps to epsilon. So I think that's why it is typed like that, as opposed to something similar to this. I guess I'll also cover calling functions as well, which is it's actually pretty straightforward, aside from call indirect. But, get this. Yeah, so the calling function is really easy. So you just call the sort of its immediate value, which is the index of the function as defined in that module. And this will have a type of whatever is stored in the context. because the context stores the types of all the functions that's in that module, so you can just access it at index I and say that it's equal to some function type tf, and so therefore you sort of have a function type tf. However, for call and direct, since you're calling something from the function table, which you don't necessarily know the type of, or it can't really statically determine the type of it, since the function table can be modified during runtime. It's a bit more complex. So for call and direct, call and direct takes in the function type that you're expecting it to be. And then this is a static argument, but then it also takes runtime arguments on the stack, or one runtime argument on the stack for the index of the function from the function table that you're trying to indirectly call. And so first you can say that you can destructure tf into this left hand side and right hand side. T1 star, 0, T2 star. And then you have to make sure that the table is populated, which the paper just notates as C subtable equals n, saying that at least some type of memory has been allocated to the table. And then this can be typed as T1 star, I32, T2 star. The I32, this is the index.
So, what happens if it's out of bounds or there's a signature mismatch? Is that going to be a
Trap.
Trap, yeah.
yeah?
So yeah, I think in the small set semantics it checks for that if if this argument is greater than n or like outside of bounds, it traps.
Yeah.
Another thing is it also traps if it's an unexpected type. So this is actually a place where WebAssembly will dynamically check the type of something. So and the reason for that is because of the very dynamic nature of call and direct and the function table. Since it can be modified dynamically.
Your program's written well, it won't, but it's hard to check for that statically.
Yeah. So I think WebAssembly stores like type information about the
Well,
type.
You can actually modify the table at runtime.
Yeah. Which is why it's hard to verify
Yeah.
statically. Because being able to modify a runtime is the point, since this is
Right.
the alternative to function pointers.
Yeah. And it also allows for things like dynamic printing and whatnot.
And C, you have to have, in addition to the table, you also have to have a separate stack for function pointers. Because,
Stack.
yeah, like in linear memory. So it's just the paper, as it says, WebAssembly is designed for languages like C and C++, but
Yeah.
it only kind of supports a lot of the features. So, yeah, sorry.
So yeah, as I was stating, so it will when you call this function, the WebAssembly runtime will have a bit of overhead where it checks the type of the function that you're indexing and make sure that it matches this type TF. If it doesn't, then it traps. And so that's how it ensures security and safety during this function. So yeah.
What about data in the first in terms of I? It's local to the instance or?
Yeah, it's local to the module or instance.
Sorry, can you wait?
You're talking about this So yeah.
Oh, yeah.
Yeah. So it's the function that's local to the instance, but it also includes like functions that you can import from other modules.
It's the ith function defined in that instance. So if you
Like an order of.
exactly from the top to the bottom.
Instead of names, you just have numbers.
Right.
Yeah. However, there's like syntactic sugar in WebAssembly
Right.
with like the $sign. I think we can label functions or locals with this.
Basically anything here that you have a number for, like globals, locals, labels, like a branch, stuff like that, you can put a $sign because having to update the number in 60 places is not fun.
Yeah. Okay. So you could use this in place of an actual number. And I think
And that information is always going to be available.
Is what?
That information is always available.
No. So when you compile it, it compiles to just the numbers, but, you have WebAssembly text, and you go from the text to the binary. The text looks like Lisp. I think I have some open here. This is the Lisp form, which is like X expressions, and then this is to me more readable version of it, and then this is like what I actually write, where it's you have dollar signs, and I have templates and stuff, but still, that's yeah.
Yeah, I think there are some like interpreters for WebAssembly
Yep.
that you could use where it will preserve this information, so use that for debugging. Yeah, so I guess we can.
It's the next one.
Yeah, next one is typing modules. So those are the typing rules for typing individual instructions. But for whole modules, if you want to link a bunch of modules into one WebAssembly
Program.
yeah,
Yeah.
we need to be able to type on modules and then check if they align with each other. And for this, the type syntax looks a little bit different. So instead of having just normal types that we had before, like function types or like the T, the TG, the TF, or whatnot, we now have export PG, export star PG or export star N. So this is how you can export. This is how the type checker exports types between modules as opposed to just the values. And then so the first rule I think is for exporting functions. So under context C, if you try to export a function with the function type TF and the local types T star, and then instructions E star. In order to type this, we first destructure the function type. So we just left hand side and right hand side. And then we append some locals to the context. So C, when we add two locals in order, we add several locals actually. So first we add the parameters to the function, which are T1 star as locals, because when you have a function in WebAssembly, all of the input parameters are stored as locals, which are stored first in the list of locals before any locals that you define yourself. And then also, since you have to specify the types of all locals that you'll use in the function itself, then it will append those. And so this is how it sort of allocates type information for all the local variables that you use in a WebAssembly function. Then it appends a label for T2 star. And so this allows you to branch out of that function. This label then denotes that if you branch out of that function, then it expects to have the types T2 star at the end of the stack. And it also does the same for the return value. Right, and since there's only one return value, this also means that functions are not first class. They can't be nested within each other. So specifies what the return value of the function that you're currently in is. And so if you call the return instruction, this will simply this is the same as doing a branch to the function level label. And so what this will do is it will just fetch whatever this type is and make sure that's something in the stack. And then this has to entail that the instructions have type export or epsilon T2 star. The reason why it's epsilon is because, like I said, the input parameters are stored as locals, so they aren't stored on the stack once you're in the function. So there's an epsilon here. So I was expecting an empty stack once you store the function. And the final export statement will be typed as a export star, and the function type. Yeah, it's pretty similar syntax for exporting globals, tables and whatnot. And the final rule over here, which I won't write in the board because it's massive, but this pretty much states that given context with list of function types TF, global types GG, table size, memory size, where all the exports are distinct. You can pretty much link into one module with all of the functions, globals, tables, and memory.
It's not growing as fast. Like if you look at JavaScript in 2017 versus WebAssembly in 2017, JavaScript's a totally different language, and then WebAssembly is still basically the same, which is, in my opinion, how it should be. But these are some of the recent changes, and I noticed that a lot of the syntax and stuff, like if we go back here, there are no more underscores except for like the sign extensions and brif and stuff. So like local.set, local.get, and then local.t and global.set, I32 load and stuff like that. They don't. They just changed some of the syntax, and there's also when this paper was released, a lot of the stuff that they mentioned here was not supported in the implementations, which was discussed in the paper, but we didn't really mess with that. So like, for example, where it says here with multi-value, they only allowed functions to have one output, and same thing with blocks and stuff like that, right? They can only have one output, which is kind of defeats the point of having a stack machine, right? And then also branches and stuff like that, they can't have, even today, they can't have inputs. So you can't pull from the stack before you go into a loop, or when you're inside a loop, right? It's kind of a limitation, but it's good that they prepared. And then the rest of the stuff is just like, oh, this was too slow, or this was inconvenient, right? And then I thought this was funny. They had this example, and they said it's expressiveness. So this is how you would implement, say, a switch statement, right? You have 4 blocks, and then you BR table to those things based on a value, right? So you have a value here on the stack, let's say. And that's not allowed, actually, but either way, you BR table there, and you branch to these, and that's how that would work. But if you look at like how it actually ends up being, they argue this is expressive, but in reality, it's not. And that's what it ends up looking like. So I think that's it.
If you can go back.
Yeah.
So multiple blocks can have. Sorry, my bad. I haven't seen the.
Yes. They kind of indentation's not great, but you know it's.
Yeah, that's abuse of formatting.
Yeah. It's pretty much it for us, I think. How much time do we have?
Oh yeah, I was gonna cover progress and preservation briefly.
Oh yeah, sorry.
Yeah. So I forgot to mention it before I ended up to get again, but so the way that they mentioned in the paper very briefly that they confirmed that progress and preservation is true. But these rules, however, they did not prove it in the paper. So I looked it up to see if someone had proven it extensively. It would be a hard task because there's a lot of rules. But I couldn't find someone who written it out fully. But I did find a paper from what's his name?
I think I have it open in one of my tabs somewhere.
It was a 2018 paper from, I think, 2018 paper from the 7th ACM SIG Plan conference from Conrad Watt, who just pretty much defined the syntax and semantics for Webassembly and then plugged it into Isabelle, which is like this proof assistant software, and then found that progress and preservation do indeed result from these rules, which therefore proves soundness. But I guess I could go over a couple of simple examples of like some of the rule induction, or not really rule induction, because these are like base cases for progress. So these are like pretty obvious, but just for the sake of understanding how it would look like. So if you, for progress, or actually let me write down the formal statements actually. So progress states that it uses a slightly different typing notation here that's more general and applies to a store that consists of multiple instances of modules. But it states that if this instance I entails that the store, the locals, and then the instructions have a type T star, then either E star is a value, which it denotes as E star equals value prime star, or E star is just a trap statement, or E star steps. S prime, which is V star, V prime star, new set of locals, and then a new set of instructions, V prime star. So that's how progress is defined. I guess with simple examples. So one base case is for const instructions. So for T const C, which has the type epsilon arrow T, we know that since it has this type, you must satisfy one of these things, and we know that it satisfies E star equals trap because this is a value, and values are defined in the paper as any type of constant value. And then a less simple example would be the block rule. So block TF function type E star instructions and so C tells that this has type function type, right? We know that this steps to a label, which then steps to a set of locals on the stack, E star, which then eventually steps to a const to a value. All we need to know is that it steps immediately to a label, which is provided through one of the small step semantic rules, which satisfies progress here. But yeah, I'm not going to go exhaustively through this for every possible typing rule. That'll take a while. That was a simple example of progress proof looks like. And then for preservation, a really simple example that I could come up with is for a binary operation. So if we were for preservation, we'd be inducting over the small step semantics rules, and one of them is we have two values on the stack, which are constants, and then we apply a binop rule, operation, and then this steps to another const. C, and then we know that this binop instruction has type T to the arrow T, and overall this would have the type epsilon arrow T, and constant values does have the type epsilon arrow C. And so this shows that actually I haven't even written down preservation, but preservation states that if instruction steps and it has a type, or if a store locals and instruction steps and it has a type, then whatever steps do has the same type. So this steps to that, they have the same epsilon arrow T type. So that's how you would prove it for just by our rule. Yeah. That's
So what do progress and preservation actually tell us? Because so normally we prove progress and preservation and say this prevents runtime type errors or some kind of runtime error. But one of the options in progress is if you trap.
Right.
So what do we actually get in terms of safety? And how do they guarantee it?
So like when it traps, it's an exception, right? So yes, the WebAssembly, you can still run functions, but it returns to the caller and it doesn't, kill your tab and crash your browser, right? So a trap is still ending the program, but it's not a fatal, right?
It's not like violating security or like letting the program access code or access restricted or like abstracted or encapsulated information from other modules that hasn't been exported. So it's ensuring that doesn't occur. But it can still trap if,
And also, there are proposals. So one of the things they wanted to do, and I'm not sure if I'm going to find it, but one of the things they're, and to do C++ stuff, right, you need exceptions, you need threads, you need all this other stuff. And there are proposals to have what you would need to have exceptions and being able to resume after traps with some handling for it. But in the current specification, there's no way in WebAssembly to handle a trap because it's supposed to be fatal, which is useful to have that. But yeah, it's something that the host has to deal with.
Yeah, an ideal thing about WebAssembly is that it can't like directly access like the HTML DOM. Which
Right.
makes you question like, oh, why do they develop this for the web if they can't access things on the web page? But the thing is that the JavaScript that's hosting the WebAssembly can still sort of communicate with the WebAssembly in a way where it like listens for output and then sort of proxies any sort of requests for DOM related information.
I actually have a demo here where I used JavaScript eval and within WebAssembly. I have to zoom in, don't I?
Oh boy.
Sorry for the mess, but you just import the JavaScript functions. Yeah, so okay. But you just import the JavaScript function and you can call it from here, and you have to have some boilerplate here, because the only types in WebAssembly are numbers, so you have to pass in the numbers, the address, and the length of the string, and the JavaScript has to read from WebAssembly's memory, extract the string, and then actually call functions on it, right? So, it's not like the paper and like most people who talk about WebAssembly say, oh, it's this new buzzword trendy thing, right? It's so amazing and perfect, but it's got some ugly parts too. But you can that's still like not as big of an overhead versus a lot of the previous solutions were to interacting with WebAssembly, where you had to like first pass it through a JSON RPC, where it has to like stringify stuff and then call it, right? Versus this, which goes straight through the same virtual machine JavaScript VM directly to it. So it's not perfect, but it's still way faster than a lot of solutions. Anyone?
Okay. I was just gonna ask, like, what is the purpose of WebAssembly? Is it supposed to be a drop-in replacement for JavaScript?
No.
Or
you literally cannot use WebAssembly in the browser without JavaScript. There's two things. One is, like I said, we're having desktop applications, and so someone made this thing called EM scripting, right? And you can basically compile almost unmodified C program, even if it uses stuff like WebGL or not WebGL, OpenGL and stuff like that, and it compiles it to ASM.js, right? Or at least in 2017 it did, and you could run that in your browser and like play games and stuff, right? That were basically not much work was done to port it, and so that was good until you like had like a garbage collection or something bad, right? So for the high performance stuff, WebAssembly Matters. So like at the company I was at, we were doing statics simulations for like architects, right? So they build a building and say, is it going to fall over when we build it? And we could do like the complex math and stuff for modeling that. And if we did that in JavaScript, it would take like 5 years. But doing a WebAssembly, not exactly 5 years, but it would be slow. Versus WebAssembly, we know it's going to work quickly, and we know that it won't take them forever to load the page because it doesn't have to compile the JavaScript and know all that stuff, right?
Because this doesn't sit on top of JavaScript. This compiles directly to the native assembly.
Right. So
whatever machine's running.
The paper actually talked about this, but when your browser downloads it, there's two ways to do it. In the example I had, it didn't do it the best way, just because it's easier. But the best way is to do what's called a streaming instantiation, right? So as you're downloading, it's reading the module as it's going, and it's loading it into memory and preparing to compile it. So what it does is it takes all the types and it puts them into a cache of some sort, and it takes all the imports and the exports and it gets their types, and then it gets the function definitions and it uses that type information as it goes. And it can do the functions actually in parallel. So like if you're doing JavaScript, it doesn't compile, it doesn't just-in-time compile things unless you run it more than once, right? Versus WebAssembly, it's already compiled as it goes, so you don't take that download hit. Like if you have a C program that got compiled to ASM.js, it's going to be very big. Versus WebAssembly, it's going to be just bytes probably. If you measured in kilobytes versus megabytes, right? So it's a pretty significant difference. In performance. They went into that in the paper.
So you don't actually, like people usually handwrite WebAssembly. Usually writing.
I'm weird because I have to, but normally you just write in C.
Compiler that compiles C,
yeah.
Whatever.
Right, it's language agnostic, although some of these proposals hint at it, and the active proposals and the ones that are getting work are even more revealing. But some languages are better than others for WebAssembly. Like for example, any language that uses a garbage collector, it's not impossible to do. It's just very hard to get it right. And because usually they just take their virtual machines, which are written in C, and just directly compile them to WebAssembly, the performance sucks. Like they just suck, and they're not reasonable. Like you'll have. Yeah, I'm not going to go into details, but like, anything with moving. So they have these bulk memory operations, and I'm not sure if those are actually available yet, but that was needed because like if you implemented malloc the way you would think is reasonable, it's slow. It's much slower. Like they said, I can't remember what statistics they said in the actual proposal, but it was like over 10% of like the total time spent in a game was in memcopy, right? Which is like not acceptable for compared to like 5% in normally, right? So there's a bunch of, it's not perfect.
WebAssembly program, when you like compile it to WebAssembly, it's going to be run by another WebAssembly runtime, right? Because it's not really, you're not really compiling.
No, well it depends. So V8, for example, this is like Chrome and stuff, right? I'm just using that because I know it. They have two different versions. They have one of them which is just an interpreter,
Right.
and it's a debugger, right? And that's the only reason it's used. But normally, when you do it, it gets just-in-time compiled to assembly for your native OS, right? So if you're on a refrigerator, it could be MIPS. If you're on a laptop, it could be x86, phone, ARM, or whatever. But it varies. So it's platform, language, target agnostic is what it's supposed to be.
Yeah, and although it's called WebAssembly, it was also designed in line with like the consideration in mind that it could also be used for non-browser purposes.
So if I call some like GPU dependent API, it's gonna
Right.
see the equivalent API immediately, and it's gonna call that.
Yeah, and when you link, I'm not sure how V8 does it, but the way it's designed, it should be able to link it directly to that function. Because if you look at the JavaScript API for WebGL, there's a lot of using like they're called array primitive or primitive arrays, where it's like float64 array, int32 array, and stuff like that, where it's JavaScript doesn't have number types; they just have floats, right? Because WebGL is inherently typed and JavaScript is inherently not typed, it actually makes more sense to use the WebAssembly version of it because it's safer and it makes more sense. And probably more performant, but it's still a little bit painful because you have to like deal with linear memory and stuff like that.
All right. So the discussion, we're out of time.
Awesome.
So thank you. That ends the paper presentations. So obviously we don't have class on Wednesday.